We have the next speaker, Apeksha Sanghi from IISER Bhopal, and she will be speaking on infinite metacyclic subgroups of the mapping cluster. Over to you, Apeksha.
Welcome everyone. So first of all, I would like to thank the organizer committee for inviting me to give the talk on my research problem, infinite metacyclic subgroup of the mapping cluster. And this problem is joint work with Pankaj Pavli and Dr. Kashyap Rajasati.
Yeah, Apeksha, there is some echo. There is some echo. Are you like using a headphone or something?
Yes, I'm using the earphone because otherwise the voice will be like. Let me just connect it with the different device.
Yeah, please. Yeah.
Just give me a minute.
Yeah, Apeksha, can you? Yeah.
So, am I audible now?
Yeah, perfect. Please. Thank you.
So, we will be going to talk about the infinite metacyclic subgroups of the mapping class group. So, let us see what these terms make the metacyclic group or the mapping class group. So, we will start our talk by defining what the mapping class group is. So, we are going to take the genus G surface to be the closed and connected orientable surface of genus SG. The mapping class group of SG is the group of homotopy classes of orientation preserving homeomorphism of SG. So now, seeing some example of this mapping class group, when we see a mapping class group of sphere, it will be always trivial. The mapping class group of torus is SZ2Z. So now, taking this definition into consideration, let us go to the metacyclic groups. So a metacyclic group is a group extension of a cyclic group by a cyclic group. That means we have a short exact sequence of this at this. So here, since we have this short exact sequence, so here we can observe that this n will be normal in H and L will be isomorphic to H quotient n. And both of them should be cyclic. So this is another way of looking the definition of metacyclic group. That is, if there is a normal subgroup of H such that when we quotient it down with that H, then we get the cyclic subgroup. And this metacyclic group is split metacyclic group if this exact sequence which we have seen above, it splits. And in that case, we are going to say that this H will be isomorphic to this N semi-direct product with N. So the examples in the previous talk, we have seen that the dihedral group, the quaternion groups, these are the examples of the metacyclic. Now, let us move to the, so here in this talk, we are interested in the infinite metacyclic groups. So infinite dihedral is one of the examples of that. In the entire classification, So the infinite metacyclic group will be isomorphic to these three types of groups. It will be Z semi-direct product Z, Z semi-direct product with Z2M with some K, and Zn semi-direct product with Z. So here, note that the first component which we are using here, that will be normal in that exact sequence. So now, as we have seen what the these terms means, so we are going to talk about the motivation regarding this problem, or what the question we wanted to address in this talk. So given two mapping classes in mapping class group, can one derive equivalent condition under which F and G will have conjugates that generate a metacyclic group? For this question, the answer to the finite metacyclic groups have been provided in these three conditions. So is my screen entirely visible?
Yeah, we can see.
I think so. Yeah, now it will be fine. I think so.
Okay, yeah.
So this question have been answered for the finite metacyclic groups in these three papers. And now we want to see about the question for the infinite metacyclic group. Furthermore, in these papers, we have given a construction of infinite metacyclic subgroup of mod SG.
Excuse me, hello.
To be precise.
Hello.
Yes, hello.
I have one question. What do you mean finite metacyclic group?
So finite metacyclic group means the order is finite.
Which order?
The order of the group is finite.
Yeah, so then you have a short exact sequence in which
where N and L both are finite groups, finite cyclic groups.
I see. Okay, fine.
Yeah. And for infinite, we need at least one of them to be of infinite order.
Fine.
So is it fine?
Yeah.
Okay. So yeah, so we are so for the finite metacyclic group in this, like in these papers, we have already assumed that if both F, N, and L in this presentation, N and L are finite cyclic groups. Okay. So yeah, now when for G greater than equal to 5, we have given a construction of infinite metacyclic subgroup of mod SG, which we will also discuss in this talk later on, what that example is. And that is in particular, it was given in the fourth paper. And now, by getting this motivation from this example, we have given the characterization of infinite metacyclic subgroup of mod SG. And this is now on the available on arXiv, this paper, and I'm going to present this papers. So yeah, so to go into this, we are going to define some preliminaries that we need to see what our main theorem is, and some examples to see how they are going to look into the mapping class groups. So first of all, we are going to define what is a multiple. So disjoint union of simple non-isotopic essential curves is we are going to call a multiple. And now this mapping class in mod SG, it will be periodic if it is of finite order. It is said to be reducible if it preserves a multicurve, and we will call such multicurves to be the reduction system of F. We are going to say a mapping class is irreducible if it is not reducible, and we will call a mapping class F is pseudo-Anosov if it has a pair of transfer singular major foliation on genus G surface. So here, this foliation on genus G surface, you can think locally it should be a foliation on R2, which we have seen in the previous talk. So yeah, this is the elements type of elements which we are going in the use. And from the Nielsen-Thurston classification, it has been seen that any mapping class will be either periodic, reducible, or pseudo-Anosov. The another way of looking this pseudo-Anosov is that it is neither periodic nor reducible. So let us see some examples of these mapping classes, like periodic mapping classes, reducible or pseudo-Anosov mapping classes. So now this in this figure, so when we are here, this F is represented as a homeo in this figure. So this F is in the mapping class group, which is represented with rotation of this polygon with opposite side pairing. So this polygon you can see in the it is like genus 2 surface when we identify these opposite sides. So this is an example of a irreducible mapping class. And for the second subfigure shows the reducible mapping class, where it is a rotation around this axis. And here we can easily see that this is reducible mapping class because this F fixes this curve C. So yeah, now we are going to see an example of a reducible mapping class, which is about the Dehn twist. So a Dehn twist about a simple closed curve C is an infinite order reducible mapping class. And how we are going to define this Dehn twist is as follows. So we have, suppose on the torus, we have these two curves, C curve and the D curve. The Dehn twist of D about the curve C will be this picture. And here what we are seeing that that twisting is only happening at the neighborhood of C. And on the complement it is identity. So this is how we are going to define the Dehn twist in any genus G surface too. So this we have shown an example for the genus 1 surface, and this same can be extended to any genus G surface. Now in this you can see that C curve is is preserved under this Dehn twist around this C. So C is a reduction system for TC. There is one more property of Dehn twist that we are going to use in our talk, which is the conjugate of a Dehn twist is GTC G inverse, and which is again equal to the Dehn twist around the curve G of C. So till here, is there any doubt? Okay. So now we will go to the example of the this pseudo-Anosov. Because their definition is little technical, we are going to give a Panhard construction which tells us that but the some particular example of the pseudo-Anosov mapping class. So to construct that example, we take some collection of simple closed curves C in SG. We say this collection of simple closed curve is filled if we cut our surface along this curve, and if we take the if you cut and then we close it, closure of this surface, this connected surfaces, then it is the union of a closed disk. So the planner gave the construction that if we take two multicurves A and B such that A union B fills the surface, and if we define F to be positive powers of TAIs and negative powers of TBJs, then this will be pseudo-Anosov mapping class, provided that each AI and BJ should appear at least once in that product. So this is an example of a pseudo-Anosov which we are going to use in our talk a lot for constructing the infinite metacyclic subgroups. So yeah, so now we are going to give an example of infinite metacyclic subgroup of mode HG with pseudo-Anosov generator. So to see this, so like we are going to define an example on the genus G surface. We have taken two multicurves A and B. Here you can see that A and B are like multicurves because they don't intersect, and they together fills this surface, genus G surface. And we are going to take the G to be the involution, which is the rotation about this axis, as we can see in this picture. Now we define the mapping class S to be this, where we are taking the positive power of TAI and negative powers of TVJ. So by panel construction, this is a pseudo-Anosov mapping class. And when we and since G fixes each curve in this A union B, from figure itself it is pretty clear. When we apply G inverse FG by applying the properties of this dent twist, so here we are going to get that after applying the property G inverse in these AIs and BJs, it will be again AI and BJ. So it is equal to F. And so from here, we are kind of getting that the group generated by this F and G, because it has this relation, so it will be abelian and it will be isomorphic to Z direction Z2. So taking the motivation from this example, we have generalized our theorem to the infinite metacyclic groups with one pseudo-Anosov generator, and that our first main theorem is. So whenever we are taking the elements in the mapping class group such that Fg is infinite, we are going to assume that F will be normal in Fg. This is the convention which we are going to take in this theorem. And now, given two mapping classes, if G is pseudo-Anosov mapping class and if Fg is a metacyclic group, then Fg will always be abelian. It can never form in non-abelian group. And now from here, since it is abelian group, this G will be normal in the metacyclic group F. So now let us see what happens for the condition that if F is pseudo-Anosov mapping class. So if F is a pseudo-Anosov mapping class, then the following statement holds. So yeah, so if Fg is metacyclic, then G cannot be an infinite order reducible mapping class. So here to see this, that we are not going into the details, but if Fg is metacyclic, then G cannot be of infinite order reducible. So this implies we are only left with the choice whether G is pseudo-Anosov or periodic. So if G is pseudo-Anosov and Fg is metacyclic, it will always form abelian group. In fact, it can never form Z direct sum Z group. So here, what we have concluded till here is that if for infinite metacyclic group, if one of the generator is pseudo-Anosov, then it will never form Z direct sum Z group, where both of them are of infinite order. And now, when G is periodic, and Fg is abelian metacyclic group, then G should preserve each invariant major collision of F. So here I just wanted to recall that there is a thing that if F is pseudo-Anosov, then there will be two invariant major collisions of F, and G will preserve each of these invariant major collision of F. And if Fg is non-abelian metacyclic group, then G exchanges those invariant major collision of F. This term I'm kind of like assuming that yeah, it will be like really technical for the time being, but you just assume that if it has some invariant major collision, then G preserve them, and or G exchanges if it is non-abelian. And this is if and only statement. The converse is also true. So now let us see one more example to like lighten up this like theorem. So we are taking a G to be the periodic mapping class, which is of order 8, realized as a 2 pi by 8 rotation of a 8 gone with opposite side pairing. And here we are taking this Ci curve to be AI plus 1. And C4 to be A4 A1 inverse. Now here, as C1 and C3 are disjoint, so C1 C3 will form a multicurve. Similarly, C2 C4 will form a multicurve. Also, the union of all of these Ci's together, they are filling S2. So now this mapping class, again by panel construction, this will be pseudo-Anosov. And now when we apply G inverse, when we apply G, G inverse Fg, because G takes curve Ci to Ci plus 1 and G takes C4 to C1. So G inverse Fg, again by applying the property of the Dehn twist, it will be F inverse. So we are going to get that Fg is isomorphic to Z semi-dark would be ZA. This is not abelian, because here the relation is inverse. Now, if we take instead of G by G square will commute with F. We just apply the power like by applying the group theoretic properties, and we can get that this will be equal to this F. And hence we are getting a metacyclic group which is isomorphic to abelian group Z direct sum Z4, that product. Now this example kind of gives us the like general version. So this we have defined on genus 2. This can be extended to genus G surface, and that is for G greater than equal to 2, there is an infinite metacyclic subgroup of mode Sg which is isomorphic to Z semi-direct product Z4G or Z direct sum Z2G, where F is a phenotype pseudo-Anosov and G is the rotation of a 4G cone with opposite side pairing. So this like completes the part for the pseudo-Anosov. Now let us see when this one of the generator is reducible, infinite order reducible. So let us start with an example with the same. So this was the example which I was talking earlier. So this is genus 5 surface, and we have taken G to be the this involution, that is the rotation about this axis. Here we can see that G exchanges this C and D. And now if we choose F to be TC TD inverse, again by applying the property, we are going to get GFG inverse is F inverse. So FG will be isomorphic to Z semi-dark for Z2. Here we can note that F will be reducible as it fixes the curve C union D. So it is a reducible infinite order mapping class. Now, taking this motivation from this example, we are going into some before going to the main theorem regarding this, we just explain some terms, and that is about this canonical reduction system. So intersection of all reduction systems for a reducible mapping class is going to be called a canonical reduction system. And now for a periodic mapping class F, we have the canonical system of F will be empty. For the Dehn twist, it will be curve C itself, from where the twist is happening. Now, for a reducible mapping class, the canonical decomposition, the Nielsen system classification gave a canonical decomposition, which is that if we take a closed regular neighborhood N of CF, and then F to the power N will be equal to this product, where these CIs are coming from this CF. This Fi is the element in mod Ri, mapping class group of Ri, where this Ri is the connected component of the cut surface along this CF, closure of the cut surface of the CF, neighborhood of CF. So, and now for least chance, and here Fi should be either identity or pseudo-Anosov. So we can take, if it's not identity, suppose it's some finite order, we can take power to be n such that it becomes identity or pseudo-Anosov. So the least n such that we get this decomposition, we are going to say that as a degree. And this component, the Dehn twist component, product of this Dehn twist, this we are going to call as a multi-twist component of F. So now, taking these notations into an account, we are going to define our main theorem, second main theorem of this paper. So given mapping classes F and G such that at least one of F or G is of infinite order, and we have degree of F and G is NNM with multiple component G's, and the CF and CG are we are going to define as these curves. Then G inverse FG, FG is metacyclic group with G inverse FG is F to the power K if and only if the following condition holds. So here CF union CG should be a multicut, our first condition that we need. The second condition is defining these AIs, BIs and CIs, which is depending on this curve CF and CG. G should take the set AI to BI. G maps BI to AI, and G fixes the set CI for every I. If F is periodic, then K to the power M should be equivalent to 1 mod N. Here M and N, recall that they are the degrees of M and N respectively. And fourth and fifth condition implies that the component of the cut surface along CF union CG forms a metacyclic group. So this is little technical, but ultimately it's saying that on the cut surface along CF union CG, that it should form a metacyclic group. So now let us see some example regarding this. So taking G to be a mapping class group, which is again rotation. Here we are going to take C1 and C3 to be two curves, which is precisely A1, A2 and A3, A4. And if we consider our map F to be TC1, TC3 inverse. So here we again by like kind of same argument, FG will be isomorphic to Z semi-dipole Z4 and FG square will be isomorphic to this thing. This can be generalized to our corollary for even integer G. So for even integer G, there will be a metacyclic group that is isomorphic to this thing. Or in the abelian case, it will be isomorphic to this thing. Now, as we have seen that the pseudo-Anosov generator does not generate Z direct sum Z group. So but in the reducible case, it will generate a Z direct sum Z or Z semi-dipole Z where K is -1. And for that, we are going to take these two involution G1 and G2. Here we can see that G1 and G2 commute. So, and if we define map F to be this and G to be this and F prime to be this. So again, by applying the property of the Dane twist, G inverse FG will be F inverse and F prime and G will commute. So we have this kind of, this we have shown for the even genus. This can be extended to any arbitrary genus. It's not only true for even genus, it is this example can be constructed for G greater than equal to 3. And now at the end, we are going to define our application, which is relating on the bound of the periodic mapping class, which generator, one of the generator which is periodic. So if F is pseudo-Anosov mapping class and G is periodic mapping class, then order of G will be at most 2G if Fg is abelian. Order of G will be maximum 4G if Fg is non-abelian. When we are taking F to be reducible mapping class, in this case, order of G will be at most 2G plus 2. And when G is abelian, when Fg is non-abelian, it will be at most 2G. And if F is periodic and Fg is non-abelian, then the order of F can be at most 2G plus 2. And all of these bounds are realized. So sorry, I like took 3 minutes extra. So, but yeah, this is my entire.
Yeah.
Thank any questions?
Yeah, Apeksha, thanks a lot for the nice talk and the nice work, of course. Any quick questions?
I just want to know the classification of groups for which the kernel is Z and the quotient is also Z. So can you just show me that slide?
Yeah, sure. Definitely. So this is it will be G inverse Fg will be either equal to F or F inverse. Nothing else can come. So
Okay.
because from the semi-direct product, we know that there should be a map from L to out of N. Since we are taking this N to be Z, so out of Z will be Z2. So we have only two maps from Z to Z2. It's for either K equal to 1 or -1.
I see. Okay.
So that is
Fine.
the main idea behind this isomorphism.
Okay. Thank you.